Welcome to our latest video on the topic of aromatic chemistry and specifically the structure and bonding in benzene. This video is suitable for A-level students. By the end of this video lesson, you should be able to explain in terms of their structure why some compounds are classed as aromatic and understand the importance of this class of compounds in medicines, biological systems, the chemical industry, etc. You should also be able to explain the structure and bonding in benzene and its derivatives and how our understanding of this has evolved since the Kekulé model was first proposed in 1865. Finally, you should understand why benzene is resistant to addition reactions. So let's start this video by defining what we mean by the term aromatic. Now, the term aromatic was first used in chemistry around the 19th century to describe a number of very fragrant substances such as benzaldehyde, which is found in cherries, peaches and almonds, and benzene, which is found when you distill coal tar. It was soon realized that these substances exhibited similar chemical properties and their behavior was different from most other organic compounds. So the term aromatic is now used to refer to benzene and organic compounds with a similar structure, and the association or link between aromaticity and fragrance has now been lost. So it's possible to be an aromatic compound and have no distinct aroma or fragrance at all. All aromatic compounds consist of rings of carbon atoms stabilized by something called the delocalization of electrons, and we're going to discuss this in this video. Now, an obvious starting point when looking at aromatic compounds is to look at the structure of benzene. Benzene is the simplest aromatic compound, and Kekulé proposed a conjugated structure for benzene in 1865. Now, conjugated means having alternating double and single bonds, and in the structure that Kekulé proposed, he suggested that there is a ring of 6 carbons. There are 6 hydrogens present in benzene as well, and the carbon-to-carbon bonds in benzene are conjugated, in other words, alternating double and single carbon-to-carbon bonds. Now, Kekulé got this idea for a ring of 6 carbons from a dream, because he had a dream about a snake biting its tail, and that gave him the idea that benzene consisted of a ring-like structure. Now, Kekulé's model for the structure and bonding in benzene is flawed, and we're going to address in this video the flaws with this model. We're also going to discuss the present thinking about what the structure and bonding in benzene is like. Now, before we talk about the bonding and structure of benzene, it's important to discuss the importance of aromatic compounds in biological systems, in industry, in medicine, etc. So in terms of biological systems, you will find that many hormones have aromatic rings, and in medicine, many drugs such as Valium, aspirin, paracetamol, ibuprofen, antibiotics, etc. all are aromatic in nature. In addition to this, aromatic compounds are also used in dyes, paints, plastics, and as additives in petrol to improve its performance. So here are some examples of medicines that are aromatic in nature. So medicines such as ibuprofen, paracetamol, diazepam, all are classed as aromatic because they have a benzene ring in their structure. We'll also find that many antibiotics, such as tetracyclines, are classed as aromatic because of the presence of a benzene ring in their structure. 3 more examples include the hormone adrenaline, aspirin, and polystyrene. All 3 have benzene rings in their structure and are classed as aromatic. So we're now going to look at the flaws in the model that Kekulé suggested, and there are 4 main problems with the model that he proposed for the structure of benzene. Now, the first problem is that Kekulé suggested that there were alternating double and single carbon-to-carbon bonds. And this is incorrect because all the carbon bonds in benzene have been found to be the same length. So that's the first problem, the fact that Kekulé is suggesting that there's alternating double and single bonds for the carbons, and we now know that all the carbon bonds in benzene are the same length. They're actually longer than a carbon-carbon double bond and shorter than a carbon-carbon single bond, but they're all the same length, the carbon-to-carbon bonds. Now the second problem with the Kekulé model is that if you suggest that benzene has 3 double bonds, you would expect it to undergo addition reactions readily. Now benzene does not undergo addition reactions unless you force it to do so. It doesn't readily undergo addition reactions. It wouldn't, for example, react with bromine water and decolorize bromine water like alkenes do. So therefore that is suggesting that benzene doesn't have double bonds in it. Now the third problem is to do with isomers. Now if you had the following structure, so let's say we had 2 chlorines or 2 bromines or 2 methyl groups, and we put that on a benzene ring. If Kekulé is right with his model, there should be 2 versions of that compound. There should be 2 isomers of 1,2-dichlorobenzene or 1,2-dibromobenzene. But in fact, only ever one structure has ever been obtained for these sorts of compounds. There is not 2 versions of 1,2-dibromobenzene or 1,2-dichlorobenzene. So that's the third flaw with this model. And the final flaw with the model is that energetic evidence suggests that the actual structure of benzene is a lot more stable than Kekulé suggested. So now let's look at the energetic evidence that tells us that the actual structure of benzene is a lot more stable than the structure Kekulé suggested. So here's the evidence. Now if we take cyclohexene, which is not an aromatic compound, it's just a ring of 6 carbons and 10 hydrogens. There's actually a carbon-carbon double bond between 2 of the carbons. And if we add hydrogen to this, we produce cyclohexane, which is C6H12. Now, when you add hydrogen to a ring with 1 double bond, around about 119 kilojoules of energy is given out when you add hydrogen to one of the double bonds. Now, if we add benzene, and Kekulé's model was correct, there's 3 double bonds, so you would expect 3 times 119 kilojoules of energy to be given out. In other words, you'd expect it to be 357 kilojoules given out. So you'd expect delta H to be minus 357 because a minus means that the energy is given out. Now, the actual structure of benzene only gives out 207 kilojoules when you add hydrogen to it. And that tells us because it gives out less energy, it's more stable than the Kekulé model. And how much more stable is it? Well, the difference between the experimental value and the theoretical value is 150 kilojoules. The actual structure of benzene is 150 kilojoules, roughly on average, more stable than Kekulé suggested. Now later in this video we're going to discuss the reason why it's more stable, and that's why we have a new bonding model that's different to the Kekulé model, which explains why benzene has this extra stability, this extra 150 kilojoules worth of stability. Now, like any good scientist, Kekulé wanted to address the concerns that were raised about his model. And he suggested that benzene exists as 2 forms, and you can see here I've drawn them here, and the only difference is the positions of the double bonds. And Kekulé believed that these different forms are rapidly changing from one form to the other. Now, this does give a reason why you only see one isomer for 1,2-disubstituted benzenes, but it fails to explain the other flaws in the model. So now let's look at the current view on the structure and bonding in benzene. Now, modern studies of benzene have shown that it's got a planar ring structure and the bond angle between the carbon atoms is 120 degrees. And the modern studies also show that benzene, like alkenes, contains a mixture of pi and sigma bonding. Now, in our last video on alkenes, we discussed pi and sigma bonding that exists in ethene. And to help us understand the bonding in benzene, let's recap the bonding in ethene and in particular focus on the pi and sigma bonding. So now let's look at the bonding in ethene in more detail, and let's also look at what we mean by sigma bonds and pi bonds. So orbitals are regions where there's a 98% chance of finding an electron, and you would have come across s orbitals, which are spherical, and p orbitals that are dumbbell shaped. And I'm drawing now the possible overlaps that we can have between s orbitals and between s and p orbitals and between two p orbitals. So if orbitals overlap like I've drawn here, this is a sigma bond. Now, a pi bond is caused by p orbitals overlapping like I'm drawing here. Now this slide shows the orbitals that are present for each atom in ethene, and the type of overlap you get between orbitals when a covalent bond forms determines the type of covalent bond. So first of all, I'm going to look at the CH bonds here, and I'm going to highlight the overlap that occurs between carbon's orbitals and the hydrogen spherical orbital. And you can see this type of overlap is a sigma overlap, and therefore the bonds that I've highlighted here are all sigma bonds. There are 4 CH sigma bonds and a CC sigma bond. So each carbon has 4 electrons in its outer shell, and 3 of these electrons are used in sigma bonding. One of the electrons is used in a sigma bond to another carbon, and the other 2 electrons are used in sigma bonding to hydrogens. So the 4th electron is found in a p orbital. This is coloured in green here, and this is at right angles to the plane of the molecule. So each carbon has 1 electron which is located in a p orbital at right angles to the molecule, and these p orbitals can overlap to form a pi bond. So the result of this pi bonding is that we have a pair of electrons, the pi electrons. Remember, there was 1 electron in each carbon in the p orbital. This pair of pi electrons are located either above the molecule or below the molecule. Now, they're easily accessible to electrophiles. Now, electrophiles are electron pair acceptors. So if you have an electrophile such as H+ or Cl+ or Br+ or NO2+, they are attracted to pairs of electrons, and we have a pair of electrons here in an alkene that is easily accessible. It's above the molecule and below the molecule. It's much more accessible than the sigma electrons, and that's why alkenes react with electrophiles. They undergo electrophilic addition. Now, alkenes are reactive because we have pi electrons that are available for bonding to electrophiles. They're easily accessible. We know exactly where they are. They're either above the molecule or below the molecule. And when we compare this later to, say, benzene, we'll discover that benzene is less reactive because the electrons are able to spread out over a ring. But here in an alkene, they're not able to spread out. They're either above the molecule or below the molecule. So they're easily attacked. And I often use the analogy that if you have an army that's all stationed in one place, in one barracks, they're likely to be attacked. They're vulnerable to attack. Alkenes' pair of pi electrons are vulnerable to attack. If they were able to spread out like they are in benzene, they're less vulnerable to attack. So now let's look at the bonding in benzene. And in benzene we have a ring of 6 carbon atoms, and the bond angle is 120 degrees between the carbons. And once again we have sigma and pi bonding. So in sigma bonding there's sort of end-on-end overlap of the orbitals. So here I have 2 s orbitals overlapping, and I can have an s and a p overlapping, and I can have 2 p orbitals overlapping. And the other form of bonding is pi bonding, and in pi bonding the p orbitals overlap sideways, and I'm going to draw this now. Now in benzene, each carbon atom has 4 electrons in its outer shell, and 3 of those electrons are used in sigma bonding. So we could have a sigma bonding between 2 carbons here, a sigma bond between 2 carbons here, and a sigma bond between the carbon and the hydrogen. So that's 3 of its electrons used. Now the other electron is in a p orbital, which is at right angles to the ring, and each one of the 6 carbons has an electron in a p orbital at right angles to the ring. Now these can overlap to form a pi bond, but instead of it just being a pi bond like this, it's possible for pi bonding to exist right the way through the ring. So I could have p orbitals overlapping with their neighbours, and this would result in rings of pi electrons above and below the ring. Now remember, there are 6 electrons present in the p orbitals in benzene, and if we have pi bonding, this would mean that the 6 electrons are in rings either above or below the actual benzene ring. And this is delocalization of electrons, because the electrons can spread out over the whole ring. And this makes the ring a lot more stable than Kekulé suggested, because Kekulé's model suggested there were 3 double bonds, and therefore the pi electrons would be in distinct regions. Now our current model for the structure of benzene suggests that rather than being in 3 distinct regions, the pi electrons are spread over the whole molecule. They're delocalized, and when electrons are able to spread out, it is a much more stable arrangement. And if I go back to my analogy of an army, if an army is able to spread out via a number of barracks, they're less vulnerable to attack. If they're all in one place, in one barracks, they're vulnerable to attack. So this is why benzene is more stable than Kekulé suggested. Now this extra stability is solely due to the delocalization of electrons. So now let's summarize the bonding in benzene. Now in benzene, each carbon has 4 electrons in its outer shell, and 3 of these electrons are used in sigma bonding, and each carbon has a sigma bond to 2 other carbons and a sigma bond to a hydrogen. Now the 4th electron on each carbon is found in a p orbital at right angles to the ring. So there are 6 carbons, and each one of those carbons has 1 electron in a p orbital at right angles to the ring. And these p orbitals can overlap above and below the ring to form pi bonds, and the electrons can therefore spread over the whole ring, over the whole structure. And this is called delocalization of electrons. And when benzene is able to spread out its electrons via this pi bonding, it means that benzene is able to become more stable. and this extra stability caused by delocalization is why benzene is more stable than Kekulé suggested. Now, we learned previously, when looking at the flaws in the Kekulé model, that the actual structure of benzene is around about 150 kilojoules per mole more stable than Kekulé suggested. Now, this is because these pi electrons are able to spread out over the whole ring. And this extra stability in the benzene structure due to this delocalization is called the delocalization energy of benzene. This extra energy, 150 kilojoules extra stability, is called the delocalization energy of benzene. Now, in Kekulé's model, there were 3 double bonds present, and therefore you'd expect benzene to undergo addition reactions, but it does not readily undergo addition reactions, and the reason is due to this delocalized electron system. Because benzene doesn't undergo addition reactions readily because it wants to maintain this stable delocalized system of electrons, and if it did undergo an addition reaction, it would disrupt the stable delocalized electron system, and the resulting product would be less stable. So therefore, it undergoes substitution reactions, because when it undergoes the substitution reactions, this stable delocalized system of electrons is maintained. Now, because benzene consists of rings of delocalized electrons above and below the molecule, this has led to the following symbol being used for benzene. The ring has a circle in it to represent the delocalized electrons, and the delocalization of bonding electrons has important consequences. Remember, it's the reason why benzene is much more stable than expected, and the extra stability means that benzene will less readily undergo addition reactions. And the rings of pi electrons above and below the molecule is the reason that benzene will react with electrophiles. And because benzene wants to maintain this stable delocalized electron system, it will undergo substitution reactions rather than addition reactions. Now, it's important to mention that you will often see people draw the Kekulé structure for benzene instead of the ring with a circle in it. And I always think of this as people honouring Kekulé for the outstanding work he did to determine the structure. However, you have to remember that benzene doesn't have 3 double bonds. It has a delocalized electron system with pi electrons above and below the ring. Now, if we look back at the 2 Kekulé forms that were suggested, the current view on the bonding of benzene is that it's in between these 2 Kekulé forms, and it's a hybrid. It's in between the 2 forms that he suggested. And if I put in the double bonds in the gaps here in one of these forms, I put the double bonds where the double bonds are in the other form, you can see that I end up with a ring of delocalized electrons. And this shows us that the structure proposed by Kekulé was very close to the actual structure of benzene. Now, it's also possible to have multiple rings, and that's what you have in arenes such as naphthalene and anthracene. And these arenes, these aromatic hydrocarbons, have similar bonding systems to benzene. Now, as we study more organic chemistry and more aromatic chemistry, you'll come across compounds such as methylbenzene, old name toluene. Now, methylbenzene is a very important solvent, and it occurs naturally in crude oil, and it's also used to make products such as TNT, explosives. Now, another example of an aromatic compound that we'll come across when studying organic chemistry is phenol. And phenol is a benzene ring with an OH group on it, and phenol is a weak acid, and it's a functional group in itself. And phenol has many uses. It's used to make medicines, it's used in cosmetics and is used to make plastics. And we'll be studying phenol and its reactions and properties in later lessons. And here are some more examples of aromatic compounds that we will come across in later lessons. So we have nitrobenzene, a benzene ring with an NO2 group on, chlorobenzene, benzoic acid, which has a C double bond O OH group on it, and benzaldehyde, which has an aldehyde group, a C double bond O and a H attached to the ring. And there are also aromatic compounds whose rings contain atoms other than carbon, such as pyridine. So now let's test your understanding of this topic with some practice questions. So here's our first practice question, and this comes in two parts, and the first part is on this slide. So the first part is asking you to describe the structure and bonding in benzene, and this is a 5-mark question, and you may include appropriate diagrams in your answer. Pause the video, have a go at this question, and then we'll look at the second part of this question. So now let's look at question 1b, parts 1 and 2. And for part 1, we'd like you to calculate the delta H for the hydrogenation reaction of benzene, which is shown here. And to do this, we've given you the bond enthalpies. So we need you to work out how much energy would be to break all the bonds, and how much energy would be given out on forming, and therefore the overall delta H. And for part 2, they've given you some experimental data, and they've said that the actual value for benzene plus hydrogen is minus 210 in this data, and they would like you to calculate the delocalization energy of benzene and explain what the term means. So read through the question, pause the video, and have a go at it, and then we'll go for the answers to both 1A and 1B. So now let's go for the answers to question 1A. So you're asked to describe the structure of and the bonding in benzene, and you may include appropriate diagrams in your answer, and any of the points that I'm going to mention now could be obtained through a clearly labelled diagram. So the first point you need to get across is that benzene has a ring of 6 carbon atoms. It's a planar molecule with a ring of 6 carbons. So you'd get that across from a drawing, or you could put that in prose. You could write that sentence that it's got a ring of 6 carbon atoms. That would get you 1 mark. For the second mark, if you would have to say that each carbon has 3 single covalent bonds, you could call them sigma bonds, to 2 carbons and a hydrogen. So if you labelled the sigma bonds correctly, or wrote down that each carbon forms 3 sigma or single covalent bonds to 2 carbons and a hydrogen, that would get you the second mark. They also allowed you to say that it's a 120-degree bond angle there as well. Now the third point, or the third mark, is given if you mention that there's pi electrons above and below the plane of the molecule. Now these are caused by p orbitals overlapping above and below the molecule, sideways overlap. There's a mark for that. And if you said these pi electrons can delocalize over the ring, there's a mark for that. And if you said that this makes benzene more stable because of this delocalization, there was a mark for that. So that's how you would get the 5 marks for this question. So for part B, you have to calculate delta H from the bond enthalpy values that you're given. So you have to work out how much energy there is to break all the bonds. So there are 6 CH bonds in benzene. So the energy required to break all those 6 carbon-hydrogen bonds is 6 times 412, which is 2,472. And then you've got 3 CC single bonds. So you have to break all of them. So that's 3 times 346. That's 1038. And then you've got 3 double bonds. So you've got to break them. So that's 3 times 612, which is 1836. And then there's 3 hydrogen single bonds, which is 3 times 436, which is 1308. So you add that up and it comes to 6654. Now the next step of this calculation is to work out the energy given out on forming all the bonds for cyclohexane. So to do this, you have to work out how many bonds there are and how much energy is given out. So there are 12 CH bonds, 12 times 412, which is 4,944. And there are 6 CC single bonds, 6 times 346, which is 2,076. Add them together, we get 7,020. Now to work out the overall energy change, we do bond breaking minus bond forming. So we have 6,654 minus 7,020, and that gives you a delta H value of minus 366 kilojoules per mole. Now if you got the two values right, so in other words the bond breaking energy and the bond forming energy, you get a mark each for that, and there's one mark for the final answer, which is minus 366 kilojoules per mole. Now please be aware that when you attempt past paper questions or you look in different textbooks, you will see the delta H value for this reaction varying, because it all depends on what values you're given for the CH enthalpies and the CC enthalpies and the C double bond C enthalpies. And therefore, in this question, you can see that you had a delta H value of minus 366, and when we discussed this previously, it was minus 357. It will be roughly the same, but there could be a slight variation in the actual number that you get. The important thing is that you use the values you're given to calculate delta H. Now, the second part of the question, B part 2, was asking you to calculate the delocalization energy of benzene. Now remember, that's the difference between the experimental delta H for benzene and the delta H according to the Kekulé structure. And all you need to do is to take the one from the other. So if I did minus 210 minus 366, I would get 156 kilojoules per mole. Now this value, as we've discussed previously in this video, is around about 150 kilojoules. And if you had to define the delocalization energy of benzene, you could either write down that it's the difference between the experimental delta H value for benzene and the delta H value according to the Kekulé structure. Another way of writing that is that it's the extra stability in the benzene structure due to the electron delocalization. So there's 1 mark for the definition of the delocalization energy of benzene and 1 mark for calculating it correctly. Using this data, it's 156 kilojoules per mole. So that concludes our video lesson. So after watching this video, you should now be able to explain in terms of their structure why some compounds are classed as aromatic, and understand the importance of this class of compounds in medicines, biological systems, the chemical industry, etc. You should also be able to explain the structure and bonding in benzene and its derivatives, and how our understanding of this has evolved since the Kekulé model was first proposed in 1865. And finally, you should understand why benzene is resistant to addition reactions. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @Chemistry.